Okay, once again, we are comparing linear, exponential, and quadratic models today. So we are going to look at some different components of each. The first is, you just told me what a linear equation looks like, and so to sum it up in one word, it looks like a line. A line, not an ear. Okay, so the model linear equation, and we use this a lot in writing the linear equations, right? Can you say it, I wonder? Y equals? Good. And what do we call that form, actually? Slope-intercept form. Good. And I heard somebody just say slope y-intercept form, and I do that tons in 7th grade because I want people to know what kind of intercept is that? A y-intercept, right? And you won't find that written in the textbook, slope y-intercept form. It'll just say slope-intercept form, right? So you showed me with your arms what it looked like. We know what the model equation is. Can anybody give me the parent equation? The parent linear equation. Chris. Excellent. Y equals x. Now, the parent equations are always the most basic, right? And so when we look at this equation, we don't even see the m and the b. So everyone tell me, what is the slope of this parent equation?
0.
Slope is 1, so the invisible coefficient here is 1, right? And what is the y-intercept?
0.
0. So you can see that that line should be crossing right through the point of origin at 0, 0, and it has a slope of 1. But I'm going to erase that because we should know that without having to see these invisible things, right? Okay, so what we're looking for is, what is the pattern in the domain and range, well, particularly what is the pattern in the range, if we line everything up in the domain. So let's make our table with both coordinates, x and y. And what numbers do we like to include when we're looking at these equations? In our domain, Abby? Good, 0, 1, 2, and also -1, -2. A couple of negatives, a couple of positives, and 0. And so just using the parent equation, this is so basic, this equation, very easy to say what y is when we plug in x, right? I mean, when x is 0, what is y?
0.
X is 1, x is 2. So everything is exactly, every y is exactly like the x. And it does give us that graph that you see here, something like that, like a 45-degree angle, right? And so now what we're doing today is looking at what is the math pattern that we can find between these points. These are consecutive points. When we look at the domain, our x values, right? Domain is here. They are simply just increasing by what?
1.
Plus 1. It's plus 1 all the way across, right? So once we know that that is consecutive, we can look for what is the pattern in the range. And so what do you see here? What's this pattern? Plus 1, plus 1, plus 1, all the way across. So what can we say about linear equations? What kind of math do you see in your range with linear equations? It's a constant addition. Another way to say that would be, what's the difference between 1 and 0? 1. And what's the difference between 0 and -1? 1. So this is actually still, this is a difference, isn't it? Or it's a constant addition. Okay? So let's make a little note here of what that is. It is the first difference. When we take the difference in the y values, we notice it's constantly the same. Constantly 1. It's this difference in the first y values that is so important today that you understand. And I know you do. This is showing us actually what part of the equation. Is it showing us, do you know, Chris? These differences, 1 and 1. The slope. Remember, it's the change in the y over the change in the x. This is 1 over 1. It's a slope, okay? Exponential. Oops, I should have asked you. With your arms, can you show me exponential? And they're looking very graceful. They're curved into beautiful curves. Okay, so there we have an exponential. Oops. Erase this and I'll put it back in a minute. Okay, so now we need the model exponential function. So I'm looking again for function form, y equals what? What is our model that we used with exponential functions? Who remembers? Remember?
Well, I
Hannah?
knew that somewhere.
No.
AX.
Liam? Oh, you're giving me the slope formula. Lexi?
All that I know is that the x is in the x.
The x is in the exponent, she says. That's true. Y equals a times
X.
b to the x. Remember that model? Okay. Maybe not. All right. Give me the parent exponential function. What would the parent exponential function be? It's going to be very basic, right, Dylan?
Y equals 1x. So, 1 to the x.
Well, okay, now, he just said somebody in the other class said as well, y equals 1 to the x. Now, if we consider that equation y equals 1 to the x, what is 1 to the first?
1.
1 to the second?
1.
1 to the third?
1.
So instead it is y equals,
2 to the x.
very good, 2 to the x. Y equals 2 to the x. And what may b never be? Remember? We showed what would happen if b was one of these numbers. Okay, b may not be 0 because 0 would cause, what is 0 to the first?
0.
0 to the second?
0.
0 to the third? Again, that gives us a linear equation. Y equals 0. It wipes out the effect of the exponent. So it may not be 0. Okay, so b may not be 0. What else may it not be? A negative. Remember what happened when we had a negative b? What is a negative 2 to the first? Negative 2. But what is negative 2 to the second? Positive 4. Negative 2 to the third? Negative 8. So we're up and down and all over. Remember when we graphed that? We used the graphing calculator. So b needs to be greater than
1.
just greater than 0. Okay, greater than 0. And it may not equal 0. So we could just simply say greater than 0, huh? Okay. And what may a not be?
0.
A may not be 0, right? Because what would happen if a was 0?
It would wipe it out.
It wipes everything out. Okay. So let's try some values in this table. And may we use the same domain? Could we have negative exponents? Yes, so let's do it. Negative 2, negative 1, 0, 1, and 2. Let's start easy. I don't know. 2 to the 0 is? Thank you. 2 to the 0 is? 1. 2 to the first is?
2.
2 to the second.
4.
How about 2 to the negative 1?
1/2.
Ooh, good job. I see you say, I hear it. 1/2. That's 1 over 2, right? So 2 to the negative 2 is?
1 over 4.
Good job. So this is how we get that exponential little curve, right? It's coming closer to 0, but never hits. You know, it's getting smaller and smaller fractions as the negative x's are getting larger and larger. But it never crosses, never hits 0 in that parent function. Okay, so let's take a look at the math now. What is going on with the points? Okay, so we do have the same domain, so we know that's just the regular +1. So this is perfect for looking at what's going on with the y values. So don't say it, let everybody find it. You should, I hope, feel familiar with this. We've done it before. What is going on here? Does it look like we're adding 1?
2.
No, we are multiplying by what? By 2, excellent. We're multiplying by 2, by 2, by 2, by 2. So we could say that the math behind exponential functions is constant multiplication. Now, there's another way to say that, which is a little harder. So I love the fact that you're thinking it's constant multiplication. But the way that the text will read is, what is 1 over 2? And 2 over 4?
1/2.
You see, and 1/2 over 1? Do you see that when you look at the ratios of each number to its next in the y's, right, in your range. 1 to 2 equals 2 to 4. Actually, 1/4 to 1/2 equals 1/2 to 1 equals 1 to 2 equals 2 to 4. All those ratios are equal. So ratios of successive y values are equal, or you could just say constant multiplication, constant factors. Okay? Okay, show me with your arms the quadratic. What does it look like? Ooh, it looks like a bunch of touchdowns. Okay, so we have the U shape, right? The U-shaped curve, parabola. And so, who can give us the model? Y equals, Tessa.
X squared must be X.
Good, and you might have a number in front of the x squared as well. So there it is, kind of our standard form model. And who can give us the parent function of the quadratic? Bella.
Y equals X squared.
Good. So small, considering most of the ones we work with are way bigger, right? But that is the parent function because it all comes down to the exponent that is what number? Squared, right? Or 2, the number 2. That's what it comes down to. So let's take a look at what happens in the range. We can use the same domain. And -2 squared, Chris.
Negative 2 squared is
-1 squared.
is 1.
0 squared.
1. No, 0.
1 squared.
1.
2 squared.
1.
So is this what we would expect of a quadratic equation? Do you see the U shape popping out in the range down here? Yes. But how do we find some kind of a consistent thing like we did in the previous, where we found +1, +1, +1, or over here we found ×2, ×2, ×2? How can we find this beautiful kind of constant thing over here is the question. And do you know, Jeremy?
Well, it's counter-reflection, isn't it?
Well, yeah, if you actually were to receive this set of points, would you be able to just say, that is quadratic?
Yes.
Yes, because you see the U, the 4's on either end, and it's coming to 0. You could. But sometimes you're going to get a set of points that is actually just part of the quadratic. And it might be like just the right side of a curve or something. And so the mistake would be somebody would, if they plotted it, plot like this and say, oh, what is that? Exponential, but it's not. And so we need to see what math pattern can be found here that would show it's not exponential. And this is how we do it. We already know the domain is a constant increase, right? They're all +1. This is all pattern up in the domain. So let's look here. Tell me, what is 4 minus 1? And what is 1 minus 0? 1. And what is 0 minus 1? -1. And what is 1 minus 4? -3. Okay, so doesn't it still feel kind of quadratic-ish here? Okay, let's try it now. 3 minus 1. 1 minus -1. 1 minus -1.
Oh, -2.
1 minus -2. -1 minus -3. 2. What do we see? Constant difference again. This is exactly like our linear, except we didn't find the constant difference until we did the second difference. We did the first difference, and now in the second difference, we found a constant change of 2. Okay, isn't that cool? It's cool that it shows up that way. So this is how you can write it. There's a pattern in the second difference of y values. And make sure that you highlight that in your notes. Really. Here we go. Before you even graph this, yes, you will have to graph a few. You guys should be pretty quick with your graphing at this point. So you should be able to do that. Before you even do it though, look at these points have been given to you outside of a table, but could you analyze that and tell me what type of equation this is without even graphing? Everybody shh, don't say it. Thumbs up when you have it. Ready? This is a exponential. Very good. You see the constant multiplication, right? The very numbers that we had just used. Okay, so now you're going to prove it by graphing, which you could have done even before naming it. And there's a beautiful exponential graph. Number 2, everyone analyze. You have a few moments. Ready? You're going to tell me by analyzing the range, y values, what this is. Bless you. 3, 2, 1. Very good. Beautiful linear equation. And so, yeah, okay, even if you're not doing the second difference, you look at this. Now, what I really should have done is put them out of order for you.
Yeah.
Because you are too smart, too bright, too quick.
Process of elimination.
But you know this is? Thank you, quadratic.
Wow, this was such a great math class.
And there you go. You heard it here at St. John's.